Hi, everybody. Thank you very much for joining. My session is about designing compensators with operation transconductance amplifiers. And we thought the reason this might be a good choice is because actually there's very little books and application notes out there. There is a couple of nice ones, one from Christophe Basso, whom I know was the keynote today. But beyond that, and one or two application notes, there is very little out there. For peak current mode control in particular, we need a type 2 compensator. We have covered this many times before. If you are an experienced power supply designer, you already know this. However, sometimes the IC contains an operational transconductance amplifier instead of a standard voltage amplifier, which we just call an op-amp. It's a bit of a mouthful, operational transconductance amplifier. We call it OTA in short. And the advantage of this thing is that it is usually cheaper. Certainly it's cheaper for the manufacturer, and they pass that cost on to hopefully to the customers also. The disadvantage is that you can't make a type 3 compensator with it very easily, because as you put the components of the type 3 across the what we normally call R1 here on a transconductance amplifier, it actually messes up the DC bias and so on. So it's not easy to use make a type 3, and therefore it's almost exclusively used for current mode applications as opposed to voltage mode applications. And then another issue is that for isolated loop design, the process is not very well defined or documented. So if you're designing an isolated power supply with an optocoupler, then there isn't, again, a lot out there giving you a nice sort of transfer function that you can stick to. You're dependent on the internal device. You have to go through the data sheet and work out what's going on. Sometimes they try to disable it and so on. So for other applications of current mode, which is basically anything non-isolated, all the non-isolated flybacks, all of the boosts, all of the CPICs and so on, it's extremely popular. We're going to design one, and we're going to use the very popular range of TI PWM ICs, which is the LM5157X range, and they have an internal transconductance amp. So let us quickly have a look at what it is all about. So this is taken from the TI LM5157 chip. This is the internals of it. You can see that they're using it for a boost converter, understandably so, because a buck would require a type 3. This particular chip has got an internal switch here, and it's got internal slope compensation, so you don't have to really worry about slope compensation. It has got internal current sense circuitry, including amplification, so that you can use a small sense resistor and your losses are small. And what is got is a transconductance amplifier, which is right there. It is normally very, very easy to quickly look at a schematic, even not the data sheet of a power supply, and say whether it is a normal op-amp or is a transconductance op-amp. All you have to do is look at the comp pin, the compensator components, and if they're tied to ground instead of being fed back into the input side of the op-amp, then it's a transconductance amplifier. The amplifier is usually drawn like this with a current source in it and an arrow, so it's 2 circles and an arrow, and sometimes also put GM on it to show that it's a transconductance amp, and GM is of course the value that they type in the data sheet, which is the transconductance of the amplifier, and we're going to talk about that in just a little bit. Before we go on, a quick word about voltage sources and current sources. Many of you are experts, so I apologize for those of you who know this stuff for many, many years. However, it's one of the first topics that we study at university, but we don't concentrate on the current bit very much, right? So typically what we're taught are voltage sources, and we do that a lot, and we talk about operation amplifiers, but that we just mean at the standard voltage amplifiers. These are covered in depth, but when it comes to current sources, they just say, oh, well, it's just a dual of the voltage source, and you divide the voltage by the resistance, you get the current because it's Ohm's law and so on, and it's kind of brushed off a little. Operation transconductance amplifiers barely get a mention even at university courses. It is not a standard voltage op-amp, and it's a current source, and its uses are quite limited. So if you can imagine, if you're going to put together a undergraduate course, you really just want to do the most popular stuff, and unless you go into power, you're not going to come across this. So sometimes it's just not even mentioned. However, in many PWM ICs, we do have an OTA. Okay, so if you have to design a compensator using an OTA, most of the textbooks and APNOs only deal with normal op-amps. There are some application notes, and there is a very nice explanation in Christoph Bassel's book, and that is the ISBN number down there that that you can use. Okay, so quick review again. I'm sorry if you already know stuff. It only be just a few seconds. Right, voltage source. An ideal voltage source provides whatever current that is necessary for the voltage to remain constant across the load. So if you have an ideal voltage source of 1 volt, is just going to give you 1 volt. If you have got 1 ohms here, it's going to give you 1 amp. If you've got 1 mega ohms here, it's going to give you 1 amp. You still get 1 volt. If you're gonna have 1 milliohm, it's going to give you 1,000 amps. You still get 1 volt. That's voltage source done. I mean, we do that a lot. We're comfortable with that. An ideal current source provides whatever potential difference that is required across your load to give you the defined current. For example, if you have got a 1 amp current source and your load resistor here now is 1 ohms, the current source will create a potential difference across RL, which is 1 volt to give you 1 amps. If you've got 1 mega ohms, an ideal current source will give you 1 megavolts in order to get 1 amp. And if you've got 1 milli ohms, it will create 1 millivolts in order to get 1 amp. So you can see that it's just a constant current regardless of the load. However, the voltage changes. Okay. Now, a quick review of voltage amplifiers. Effectively, a voltage amplifier, an ideal one, right, is a controlled voltage source. So it is going to give you whatever current that you need in order to give you the voltage that you need. And of course, you control the voltage that you need. Right? And that's why we use it for a compensator. A transconductance amplifier, the output is a current and it's not a voltage. So to make a voltage amplifier, you first have to convert it into a voltage. To make an OTA equivalent to a standard op-amp, all you have to do, provided that you don't have many components here, is you take this point, you cut this point here, right, and you connect it down there. So if you imagine this R2 here, I've disconnected it from here, and I've brought it down and connected it to ground. Okay, the output of the OTA is the potential difference between this non-inverting pin here, that's your reference, and that will be internal to the chip. I will put the schematic of the chip up in a second. And the inverting pin, which is here. So the difference between these two, multiplied by a constant, and we call that transconductance, or GM, of the amplifier, and that is specified in the data sheet, and you can see that the output is a current. So if I want to get a voltage out of this, which I do, because that's what I need in order to create internally to go to the comparator that's going to create my PWM, then I need to convert this current into a voltage, and we do that by tying this to ground. The current flows out of here down through here, and a potential difference will appear across this R2. Okay. So your transconductance is the only thing that you really need, because you know internally this reference, you know the voltage here, and this is defined in the data sheet. You can calculate the current, therefore you can calculate the impedance that you need. So how do we make a compensator? As I mentioned, for type 2, it's quite easy. All you do is you take this point here, with X on it, you disconnect that, and you twist it 90 degrees, and you connect it down here. Okay, so this is a standard voltage amplifier. You can see that the compensator components are tied into the inverting pin. This is a transconductance amplifier. You can see from the schematic, it's got 2 circles and an arrow on it. That's your current source. Usually we write GM next to it to show that there is a gain of GM associated with the output, but the components stays exactly the same. So there's really nothing scary about the type 2 made out of a voltage amplifier and a type 2 made out of a transconductance amplifier. The calculations change a little bit, but I'm going to give you the equations in a minute. But note that you cannot make a type 3 out of it, because as soon as you put compensating components around here, then it is not that easy just to stick them on the output and create a voltage from the current that is coming out of the output. Right? Again, I've got two nice references down here if you want to have a little more of a detail read. So all we have to do is derive the transfer function of our type 2 compensator, and luckily this has already been done in Christoph Basso's book, and we have taken it and we've put it into WDS. So if you have got a copy of WDS, and everybody who is joining this webinar gets a 6 months free license for WDS, you just go and you select transconductance amplifier, and all the equations that I'm going to give you for completeness anyway are pushed into the software. Right. To give you a real life example, this is taken from a TI EVM, which is available for sale. You just type LM5155 boost EVM and you'll find it. And I've also given you the link down here. It's very, as I said, it's very, very easy to work out whether it's a normal transconductance, sorry, it's a normal amplifier or an OTA. All you do is look at the output of the op amp, and if the compensating components is tied to ground instead of being fed back to the input side of the amp, then it's transconductance. Okay, so a review of a standard type 2 compensator. Here's the transfer function. Again, we have done this many times and there are videos, and this part is very well documented. You can find that very easily. You have two poles and you've got 1 0. This is one pole, this is another pole, this is 1 0. This is your pole at origin. That is the integrator. So that is the part that is the integral action that gets rid of the steady state error. This is your second pole. We usually use this in order to cancel the ESR 0 of our compensator, and that is our pole, and we usually place that to give ourselves a little bit of phase boost in order to get a bigger phase margin. This is very, very common for flybacks, boost, anything current mode, but is not suitable for voltage mode power supplies, which would be typically either a buck or some types of forward converters. Typically, we start by placing the positions of poles and zeros. During our workshop, we'd say how you do it by hand, but again, WDS does this for you. And then you select R1 and RB. This is a step-by-step, right? Typically, then, after we place the poles and zeros, saying, okay, I need a pole at this location. I need a zero at that location. Then I know my pole positions, and I just need to calculate the component values. And we often start with R1 and RB, which I'll explain a little bit later. Here, WP0 is the pole at origin. WP2 is our second pole there. Sorry, second pole. Oh, I apologize. Pole is down here. Zero's up there. Please. Everything that I said, zero was a pole and a pole was a zero. My mistake. And this is the equation for my zero. Note that these are in radians. If you wish to have them in hertz, which is what we normally use, you just need to divide them by 2 pi. Okay. And then this is the Bode plot of that compensator. I'm going to get it right this time, right? Okay, so this is my pole at origin. That is giving me this high gain, which is rolling off, right? And I've got a 90-degree phase loss. That's the result of this pole at origin. Then I'm going to hit my zero, which is up here, not down there. So this is my zero, and a zero flattens the gain by 20 dB, a right-hand plane zero, and gives you a phase boost of 90 degrees. So you can see that the gain is flattening and the phase is coming up. Right, and then you hit this pole, and when you get the pole, and it's like a low pass filter, it's going to your gain is going to go down at a rate of 20 dB per decade, and then you're going to have 90 degrees of phase loss. So this is what we get from a standard voltage amplifier, and what we're about to design is going to be an OTA version of that, and we need to get exactly the same shape because that is the compensator that we need. So let us do the same thing with the OTA. As I proposed to you earlier on, all you had to do was take the compensator components identical to type 2 and just shift them and connect them to ground. And transfer function stays exactly the same, obviously, because we need a type 2 compensator, but the equations change. Okay, these are in hertz now. So again, you can see that I have got a pole at origin. I have got a 0 up here, and I've got another pole. And these are the equations of my poles and zeros. These are in hertz now, and you can see that I've divided them by 2 pi. Okay. First, you can either place these by hand, depending on a compensator, or you can use the Biricha WDS or whatever else software that provides you out with the poles and zeros that you need. And then, therefore, we know position of our 0, we know the position of our pole at origin, and we know the position of our second pole. Let's say for simplicity, pole at origin turned out to be 800 hertz. The second pole is usually on an ESR 0, let's say 10 kilohertz, and this is the second pole, and then the 0, let's say, was, I don't know, whatever, the 2 kilohertz. So you know this one, you know this one, you know this one, right? GM is the transconductance operational amplifier, and that is defined in the datasheet. I'm going to show you a sample of the datasheet in a minute. It is typically displayed in millivolts per amp or microvolts per amp or microsiemens, and in the older devices, mhos. Mhos is the reverse of ohms because it's volts per amp. It's volts per amp as opposed to amps per volt. There you go. That's GM. So you know that one. Then you start with selecting R1 and RB. You know the reference inside of your chip, which is, let's say, again, for simplicity, 1 volts internally. If this is 10 volts, you want to divide by 10 so that these two are equal to each other. And we typically choose these values so that the current through them is bigger than 100 microamps. Magic number could be 10 kilohertz, 50 kilohertz, 100 kilohertz. But if you make these two, and you still get the potential divider equation, but if you make these two very big, the current through these will get very, very small. And if the current is very small, when you go to the EMC test chamber, it will be susceptible to noise. So when they radiate your product, it may fall over. And that's why typically you select it so that it's bigger than 100 microamps going there to give yourself a little bit of immunity when it goes to the EMC test chamber. So you know that at what voltage you want at this point, it has to be equal to a reference instead of the sheet, and you know that the current has to be bigger than 100 microamps. So you can very easily calculate these two, after which you have got 3 equations, 3 unknowns. You can calculate the rest, and of course WDS will do the rest for you. So then we know everything, we can calculate them. So that is the process that is done by hand. So I'm going to give you a design example short. Now, so let us design a boost converter in continuous conduction mode, right? I have got this is specification, 5 volts in, 9 volts out, and 1 amp. So I'm going to go to WDS now, and I should have one open. Oh, where's WDS? WDS, there you go. That's an OTA boost. I gave up the final punchline because you can see that it's matching. So that is my loop. So my input voltage is 5 volts. My output is 9 volts, 1 amps. There is no transformer. My switching frequency is 300 kilohertz. I'm going for a 2 kilohertz crossover with a phase margin of 75 degrees. The reason I'm going for 2 kilohertz is because, as you can see from here, WDS is telling me that I have a right-hand plane 0 in my boost converter of 40 kilohertz. I want to be at least 1 decade below that, so I could have gone up to 4 kilohertz, but I've selected 2 just to be conservative and make sure that everything works really well for this demo. Then these values are from the internal switch. So you know the on resistance, that's from the data sheet of your device. In my device is actually internal switch, and these are roughly defined in the data sheet as how long it's going to take to turn off, turn on, and how much output capacitance it has got. Then WDS tells me that I need a 14 microhenry inductor. I actually gave myself 10 microhenries. It made the the slope a little bit sharper and the peak of current a little bit more, but I don't care. And then I have got 440 microfarads of capacitance. WDS has calculated 434, so that is 2 times 220 microfarads. And I have measured the ESR, which we have done videos on and we've done seminars on, and there's lots of app notes. You know how to do that. The total ESR at my crossover frequency is 17 milliohms. Then we come to the controller tab. Now here, these are pretty much taken directly from the datasheet, right? So it is the current gain. We just released a video on current transformers, and we've got a few more about how you work out the current gain of your transfer function in a current mode power supply. But this is off the datasheet. The amount of ramp for this particular chip is fixed at 500 millivolts, which for some applications may be too high, because, for example, for this one, you only need about 100 millivolts. But again, we've got another video which talks about what happens and what you do if your amount of the slope compensating ramp is too much. And here, WDS has calculated the positions of poles and zeros. So if you remember the slides that I showed you, now you know the positions of the poles and zeros. We have got a passing 500 microamps down that potential divider. As I said, we want it to be more than 100 microamps, and based on that, WDS has calculated all the values, and I've gone and soldered whatever I had nearest preferred values that I had, right? And I've got myself a power supply. I'm going to do a demo. I'm going to do a demo in a minute. So we've talked about this. Okay. That is a transconductance amplifier. WDS has now calculated R comp and C comp, and what here is defined as RF BT and FBB, right? And that is here. So R1, RB, if I go to the circuit, is this lot, and these are now taken and connected to ground. Okay. So this is taken from the datasheet, including that so that you see that everything that you need is actually available. So a slope is added internally, 500 millivolts. That is in the datasheet. There you go. You will find that in a datasheet, which is referenced down here. Then the op-amp reference voltage is right here, 1 volt. So that's what we put into the WDS. So that's also available from the datasheet. The current gain is defined as ACS right here, 0.095, which I had typed in as 0.1 just to make it simple. Again, it's available in the data sheet, right? And as important as everything else, it's the transconductance given in, oh, I made a mistake, micro amps per volt, or Siemens or Mohs. I'm sorry, it was volts per amp on the other slide. We correct that in the annotation before we release the video. And the transconductance is given as 2 milliamps per volt. Yeah, and that is what we put into the into WDS. Okay. Just a hint, sometimes the dimensions that are in the datasheet are not exactly the same as the dimensions that you have in your software. So please just make sure that they are the same. For example, I think in WDS we use microamps per volt, and here they're giving it milliamps per volt, so I just had to multiply by 1,000. There you go. So I have multiplied it by 1,000 to 2,000 microamps per volt, or micro Siemens. This is the current gain, which I typed in here, and the reference. So everything that WDS needs is available in the datasheet. Now, based on that, WDS placed the points and zeros, and based on that, we got the component values, and our design was complete. Now, this is what it looks like. I've got that just over there, so I'm going to go and give you some experimental results in a minute. Unfortunately, I don't have a camera to can swing over there. So you're just gonna have to watch it and listen to me. But just bear with me 1 second. So that is the board. That's the boost converter. I'm going to measure the loop first. This is the schematic. This is my injection resistor here. This is R1 and RB. R1 and RB, right? Then on RB, I usually put a tiny little capacitor, very small value to take out some high frequency noise. You don't want that value to be big because it will upset the beautiful control loop that you have designed. The output of the comp pin is right here, and you can see that these components are now tied to ground, and this is a type 2 compensator. Okay, so I'm just going to quickly go over there, and I'm going to set it up. Let's have a look. So let's go to, bear with me 1 second. Okay. Can you see these guys? Yes? Just nod. Yeah. Cool. Okay. So this is the compensator that I'm measuring on the boost converter that we just designed, right? And I'm going to now import that into WDS, and I'm going to superimpose it on the theory, and hopefully, fingers crossed, it's all going to meet. So save. And then I go here into WDS, frequency response, file, import, body, and I go to desktop. Okay, that is compensator. And I want to look at there you go. Right. So here, the red trace is the simulated compensator for my transconductance amp as per the values that we put into WDS, and the black trace is what I have just measured on the real board. And you can see that I've got a really lovely and beautiful and close match. I have not cooked these results. Honestly, this just came out with the values that I put in, and I was pleasantly surprised how close it is, right? The phase is almost perfect. The gain of the compensator is a little bit off. However, the gain of the plant is also a little bit off. Look at that. The gain of the plant is all a little bit off in the opposite direction. So when I actually add the two together, I get a near perfect match, right? That doesn't happen all the time. One error is correcting the other error, right? So this is just pure luck. However, you can see that we have got a very, very close match. In particular, what we're interested in is the compensator. So let me show you that one more time. There you go. That so comes to show that the equations are correct and it matches very well with the theory. Okay, so then okay, this is just what we talked about. With regard to the shape, is exactly what you expect. So that is your polar origin. So again, okay, and then it flattens because of the zero, and then that is another pole. Again, with the phase, polar origin gives you 90 degrees of phase loss, goes up because of the zero, and then it comes back down because of the second pole. So we've got it's working just like we expected. Okay, and this is the measurement that I've just done. That is your body 100. This is your injection resistor. To measure the compensator, you put the channel 1 here on top, just at the bottom of the injection resistor, and you put channel 2 there, just on the output of the transconductance amplifier, and then you get the measurement that you want. Okay. If you wanted to measure the plant, then channel 1 goes there, channel 2 goes there. Again, you can download this later, I believe. So it's there for you if you need it. And then this is the plant, which I showed you. It's a little bit off, but luckily in the opposite direction. And then finally, to measure the loop, one goes there, and you're measuring all of that. And you get the very nice, perfect match that we have here. And basically, that's it. I hope you enjoyed the webinar, and I wish you all the best and hope to see you at one of our workshops.